communicated some of the references of my work if you are interested. And so the static scene analysis part, the dynamic scene analysis part, the action understanding part, and so on and so forth. Knowledge representations. So if you are interested into taking into account this approach, here are some references. Okay, I would like to thank you for your attention. I'm trying to be fast,
yeah.
so I prefer to have some kind of discussion.
Yeah. Any question? Well, I have a question first. I think the theoretical framework is quite clear. It's just now, what's the current stage in the robot?
Yeah. No, actually, this architecture has been built by not taking into account robot. Now we are completely moving to this, to the robot, to the pepper robot. So now we have a pepper, and we are completely moving this one. So we are renovating. We are completely renovating this kind of architecture. So we are moving from the computers from the architecture in a computer to the architecture completely in a robot. So we are at the early stage in moving into the robots. We have pieces of software that we may reuse and so. So for example, the parts related with the symbolic part. It could be, for example, I'm very interested, for example, in investigating the role of NARS in this part. So instead of taking into account the typical KL1 system, the typical typical knowledge representation system, maybe a more flexible system like NARS could be more useful for us. And it's interesting that by taking into account this intermediate level, and we have the symbols at the symbolic level are firmly grounded into the geometric space. So this is in my opinion, the introduction of this intermediate geometric level could have grounded the symbols into a geometrical entity, which is more easy than grounding the symbols into a sub-symbolic level. So it's a neural network.
I just have a comment, I guess. So, based on what you're saying about a conscious robot, even down to the level of its architecture, like what CPU it has, or even what software is driving its consciousness, like NARS or SOAR or anything like that, or even what language those things are implemented in, Java versus C versus Clojure, all that will affect the robot's self-perception.
There are many problems from a computational point of view. The current implementation is made up by using we use a kind of list for the knowledge representation system. Actually, we use a system which is called a loom, a powered loom or whatever. So it's a knowledge representation system in Lisp. And then we use currently we use our Lisp for the Lisp or Java for the intermediate level. And then we use neural networks for the sub-symbolic level. Actually, the robot is you take into account the fact that the robot have a Wi-Fi. So the robot is is an entity, is a computer network. So it's not necessary to have the computation on board of the robot, of course. So typically, the typical strategy is taking into account is to have some kind of processing, the camera processing on board of the robot, and then to upload the results into another computer and so on. So the computation from the computer point of view is not necessary to be internal of the robot. So we may use but the robot has a Wi-Fi. So but anyway, it's interesting to take into account. For example, we were discussing about the robot resources. So how much of the resources do you live to to the vision system or to other systems. So, for example, we consider one of the previous slides was related to the botanical garden. Okay, and this was a problem because at the botanical garden there is a large basin full of water, and so when the robot was near the basin full of water, of course, all the computational resources were dedicated to the laser, to the laser, to the cameras, because it was necessary, of course, for the robot to avoid to fall down into the. So it's difficult to say. I can say which are the computational resources. So it should be necessary to have some kind of right allocation of resources depending on the needs of the robot from time to time. If you can maybe comment a little bit about the role of learning. So kind of where in this setup you include learning and the ability to adapt. Yeah. Yes, actually in the current architecture, the role of learning is mostly related with the focus of attention, in the sense that okay, there is this kind of expectation. So, in order to interpret the scene, to interpret a scene, the robot have to insert. So in the case of the focus of attention, so the robot looks for a complex scene where there might be many elements, and the robot should describe the scene. So the idea is understanding the scene. And so this is a mix of previous knowledge that we name the linguistic expectation. So for example, an hammer is defined as something which has a handle and a head. This kind of handle and this kind of head. This is a definition, so it's a kind of prior knowledge. But this is only a part of the knowledge of the robot. The other part is related with what the robot learns. So the robot learns that typically in a hardware scenes there are hammers, there are nails, there are wherever, and this is learned by the robot. So the robot learns to associate entities with other entities. This is in our architecture, this is currently the part related with learning. So the association of objects is in a typical hardware scene. There are hammers, there are nails, there are bolts, and so on. In another context, there may be other objects. An interesting thing to explore, and there are some literature in the field, is the role of neural network in building this kind of conceptual spaces. So, but we have not explored, but it's interesting. So, where do the conceptual space came from? So, how can we decide that the conceptual space of text, for example, the conceptual space of color, the conceptual space of where do these dimensions came from? So this could be interesting, for example, taking into account all this discussion from the evolutionary point of view. There is a huge field of evolutionary robotics, for example, that may be interesting into this field. So how do a baby robot, a kind of baby robot, learn how many dimensions there are in the space, how many dimensions there is in the colors, and so on and so forth. So this we have not explored this one, but I think that we can take into account, for example, the self-organizing maps, core and network, sort of. A typical way to implement the conceptual space is by considering the Conan maps, the self-organizing map or some subsymbolic system, which is able to create a kind of topology. And this could be an interesting field. And even, of course, the learning of the linguistic learning, which is a very complicated part.
So the idea would be to have a fixed conceptual area, and
Sorry.
so the idea would be to have the conceptual area fixed in the beginning, and then different things like a hammer
Yeah.
have different properties in the different parts of the conceptual area, like
Yeah.
color and shape.
Yes, no, the conceptual space in the current version of the architecture is fixed. So we take into account the conceptual space of color, the conceptual space of taste. We are not taste, but in theory we can. So our conceptual space is the conceptual space of shapes. So our point in the space is our point is a shape. So we have a fixed conceptual space of shapes. So each point is a shape in the case of static scene. In the case of dynamic scene, we have a fixed conceptual space where each point is a moving shape. So it's a shape with its own movements, for example. And in the self-consciousness part, what is it? In the self-consciousness part, each point is a conceptual space situation. So because it is a conceptual space, a higher order conceptual space, so each point summarizes the conceptual space of the robot. So it's a kind of, the robot is as if the robot look at itself from the outside. So some kind of allocentric view. So we have the egocentric view of the robot, which is considered into the lower part of the lower conceptual space. So the robot look from the egocentric view. And the higher order conceptual space is a kind of allocentric view of the robot. So if the robot is looking itself from the outside. So it is a kind of imagination that we may have. So I may imagine myself in front of you, talking to you as if I were on the outside, on the roof, for example. So the allocentric. So these are different kind of conceptual space. The shape space, the moving shape space, and this kind of situation space. But they are all fixed. It would be interesting, as I mentioned before, it would be interesting to investigate on the possibility that the robot will build this kind of conceptual space by itself. But currently it's given. Yes.
Could you please go to the next slide?
Yeah. This one.
Not this, maybe next.
Sorry?
Yeah, the next. I see one slide. Yeah, this slide.
This one.
I'm curious about how the robots can do the reasoning. Within the last point in this slide, I can do this because, and I failed because.
Yes, I can do it because, in the sense that the robot has the knowledge of itself, so of its own body, for example. So if I ask the robot, pick up an object which is too high, for example, the robot knows its own body, knows the dimension of its own body, because it knows the superquadratic described. So the robot might say, I can do it because I'm not able to pick up because it's too high for me. So this is an example for robot. Or for example, if I ask the robot to pick up an object, the robot knows that it can pick up only some kind of objects. We say, I cannot do it because of it. And it is, or for example, some most trivial examples are, I cannot do it because my battery is down. So these are, because the robot knows its own body, knows its own dimension, so it can analyze its possibilities with respect to the task. The second part is, I failed. The robot can analyze all the course of events. As I mentioned before, the robot could, like in this case, could analyze all the situation and all the actions that brought the robot to a failure, and then he can say, I failed because at some point the object fell down or the object broke, and so on. So the robot can look at its own history, and then it could reason about its own history. It's something related with the, you can read this picture even in terms of episodic memory. So I look at myself at 1 second before, I look at myself 1 second before. So I have a kind of episodic memory of my story, and then I can analyze my story. So I failed because at some point I had to pick up an object, or I get the wrong object or something like this.
Do you think that from these failure cases, then the robot would then have the ability to learn?
This should be interesting. This should be an interesting evolution. Not in the current, but it would be an interesting suggestion. So learn as we do, learn from failure. This could be an interesting suggestion.
Maybe I can add one more question. So I kind of, I wanted to get your take on how. So this type of research, it's really core, hardcore artificial intelligence research, right?
Yeah.
Now recently we see that, more and more people that talk about deep learning and neural networks are getting into place. So I just wanted to get your kind of perspective. Do you think those two fields are separate, or do you think at the end they will merge, or what is your perspective?
No, my idea is that there is some kind of merging, because deep neural networks are very effective into the problem of recognition. They are very fast, they are reliable, recognizer. They recognize almost everything. But reasoning, but intelligence reasoning is not only recognition. I know that there are some people, Bengals, for example, thinks that everything is pattern recognition. Every kind of intelligence is pattern recognition. But I'm not convinced that everything is pattern recognition, and I think that intelligence is made up by many parts. And the interesting thing in my proposal of architecture is that it's quite easy to merge different aspects of intelligence, because we may imagine that the deep learning part is the subconceptual part, where there is deep learning to recognize a very simple object. We have a symbolic part, which is the highest level part. And I think that some kind of intermediate level of representation may be useful to merge the symbolic with the subsymbolic. And so I think that we need something which merges the good old-fashioned AI, symbolic AI, and the deep neural network, which is a big problem today. I think that we need some kind of intermediate level that may, even there are in many papers, in many research, emerge this kind of intermediate level, the perception level of representation. I don't know. I need this kind of intermediate level, putting together what is beautiful into the symbolic, in the symbolic approach with the deep neural network. So I think we will converge to a kind of mixing.
Maybe I have two sub questions. So people, for example, talk a lot about those distributed representations, right? So this is kind of reminds me of what you're saying. You can this geometric representation, right? So there is there are results that we can represent different types of complex objects as vectors, right? And then I'm kind of wondering, look, from my experience, you can go to that stage easily, so you can learn how to represent objects as vectors, but then after that, there is this gap between how to use it to really start reasoning about basically kind of how to put that reasoning layer.
Yeah.
So, but in general, so if you know people from neural networks, they would tell you, well, okay, so brain is nothing but really a big neural network. Right?
Yes.
But eventually, we are able to do the symbolic reasoning. We're able to do reasoning, right?
Yes.
So when kind of so again, it's just the question: what is in your mind? What is really missing? Kind of what is the missing link between kind of representations that, let's say, neural networks now are able to do, and really kind of symbolic reasoning?
No, actually, I think that is a kind of perspective. So, if you look at the brain, and you are near the brain, very close to the brain, you see networks. You see neural networks. When you are far from the brain, you can see symbols, actually. But there is an intermediate level when you can see geometrical entities. So you may reason in terms of geometry. And in fact, consider, for example, this recent paper by the group of Harry Markham. Those papers. So there is a paper from Harry Markham. Harry Markham is very famous in Europe for the European Brain Project, for example. So according to his model, there is 11 dimensions in the brain, essentially. So the brain could be explained in terms of a kind of space, a very complicated space made up by, if I remember well, 11 dimensions or something like this. And some of you may know Chris Elias-Smith, which generated, he proposed another cognitive architecture made up by semantic pointers. Semantic pointers are based on some kind of geometry. And Peter Gadefors, of course, and even in terms of real consciousness, Giulio Tononi, which is the father of integrated information theory, proposed a kind of geometry of qualia, which is one of his papers with David Balduzzi. And so there is also the qualia space. So the idea that at some level you may describe the neural entities of the brain in terms, you may abstract the neural entities in terms of geometry, it is an idea that it can, in some sense, is emerging. So it's a kind of perspective. So what do you want to represent? You can represent, if you want to represent the brain at the very low level, you need neural network. If you want to represent some kind of reasoning, you need symbols. But there is some kind of geometry that may be in the middle.
I think we will stop for now. I think the speaker again.
Thank you.
For those who you don't know, this afternoon we actually have 3 events in sequence. Next time I'm going to give a talk about my